7.6 is about exponential functions. An exponential function, by definition, is a function. And remember, a function means that each x value has only one y value. If you guys remember doing the vertical line test, any vertical line that I draw throughout here, take that vertical line and slide it anywhere throughout this curve, it only intersects one time everywhere. Okay, so this is a function. So that's what that is. But it's of the form y equals a times b to the x. Okay, this a will be something we address later, but this b to the x is really the important part right now. And basically, it's the way you're going to recognize an exponential function is that the variable is in the exponent position. Things that are exponential are going to show this curve, okay, whether it be increasing, so we would call this exponential growth, okay. This one here is unique because it's essentially a reflection across the x-axis. Still exponential, but we don't call it growth or anything like that. This one here would be what we call exponential decay. But the idea is as we're moving to the right on the x-axis, your y values are going up, but they're going up in a much faster way than if the equation was like y equals 2x. Or y equals 2x would be something like that, okay? But the curve is getting larger much faster. If we compare, sorry about that. If we compare like a x and y chart of y equals 2x and y equals 2 to the x. So let's do y equals 2 to the x first. And then let's, beside it, do y equals 2x. So y equals 2x. So if I'm going y equals 2 to the x, what this is, so if x is, let's just say x is -1, we would rewrite, so this would be 2 to the -1, which from what we've talked about so far this week and last week, that would be 1/2. If I go 0, this would be 2 to the 0, which we know is 1. If I choose x to be 1, it would be 2 to the first, which is 2. If it is 2, it would be 2 squared, which is 4. So 3 would be 2 cubed, which is 8. 4 would be 2 to the 4th, which ends up being 16. Okay. If I do the exact same thing for y equals 2 to the x, so -1, that would give me 2 times -1, which is -2. 0 would be 0. 1 would be 2. 2 would be 4. And right here is where we're going to start seeing things get a lot more different than what this is. So if I go 3, then this would be 6. If this is 4, that would be 8. Okay? And exponentials, you can see then, an exponential, for instance, when we go from 3, it's going to give me a y value of 8. The linear function gave me, when it was 3, gave me a y value that was smaller than 8, which was 6. When I go to the next, so I increase here by only 1. Only increased by 1, but you see how this doubled. They went to 16. This increases by 1, but that only goes up by 2. Okay, so the increase in y values for exponentials happens so much faster than the increase in the y values for something that is linear. Just kind of giving you maybe something like this: y equals 2 to the x and y equals 2x. So those are the two lines that we're talking about, Okay, or comparing in that last image. And you can see that if I choose an x value of 3, you can see that the exponential, where my cursor is, has a y value of 8, and at 3, the line has a y value of 6. So the exponential got to a larger y value faster than the line did. Okay, if I want to get to 16 on the exponential, okay, I only have to go out to an x value of 4, but on the line at an x value of 4, the y value is only at right here where it would be 8. So all exponentials that we're going to talk about are going to be like that green one. Okay, we can change it a little bit. We can go like y equals, we change the base, so 3 to the x looks very similar. Okay, it just gets kind of taller, faster. Okay, so we're hitting larger y values quicker than we are for, if I square 3, it gives me 9, and 9 is a much larger y value than squaring 2. So that's why, so at an x value of 2, right here we're at 4 on the green curve, which was 2 to the x. But up here we'd be at 9 on the blue curve. So that 9 obviously is much bigger than the 4. And we can keep doing that. Y equals 4 to the x, gives me that orange one. Okay, y equals 5 to the x, gives me that purple one. And those are very similar looking curves. They all kind of do the same thing. These curves that do this behavior, like I said, we call them exponentials. One key point that we're seeing here that is very nice is the point 0, 1. That shows up on all of our exponentials here. And that's a property that we like to recognize. If we take, so these are just some different things that we can do with exponentials. You see here that this curve here is y equals -2 to the x. So that would essentially be taking all of these values here and negating them and plotting those ordered pairs. So we would have -1, -1/2, and if you see, so -1, -1/2 would be about right there. We would have 0, -1, which is about right there. We would have 1, -2, which is right there. We have 2, -4, which would be, kind of down here. So you're seeing these ordered pairs show up, and that's how we get that smooth curve. If I want ultimately what we call exponential decay, so we're going to actually get smaller and smaller y values, that means this number that I'm raising to this variable exponent, this number is going to be a number between 0 and 1. And the idea there is, if I have, let's just do some x's and y's here. If I go, let's do x. Let's do x equals -1 again. So if I go 1/2 to the negative first, let's actually give myself a little bit more room here. If this is x, that's y. We're going to go 1/2 raised to the x. So let's choose -1. So what that's going to look like is 1/2 raised to the -1. And just going through the laws of exponents that we've talked about in the last couple of days, this is a power to a power, so it's going to be 1 to the negative first over 2 to the negative first. Those are negative exponents, so we don't like them, so that -1 is going to come down here. That 1 to the negative first is going to go down there, and 2 to the negative first is going to go up there. Well, that gives me then 2. So we should see at -1, at the x value of -1, we should get a y value of 2. And that's what we get right there. If I try 0, so I go 1/2 raised to the 0, and we know anything raised to the 0 power is always 1. So we get 0, 1. If I try 1, I would get 1/2 raised to the first, which is just 1/2. So 1, 1/2. If we try 2, be 1/2 raised to the second, be 1 squared over 2 squared, which is 1 1/4. So there we're at 2, 1/4. And we can keep going. We can go into 3 and 4 and 5. We can also go to -2. Let's just do -2 real quick. And that would be, so it would be 1/2 raised to the -2. So power to a power would look like this. 1 to the -2, we don't like that. We're going to put that down here. 2 to the -2, we don't like that. It goes up here. So it gives me 4/1, which we're seeing as that point there. Okay, so that's kind of how this curve is generated through choosing particular x values. So that's kind of a brief, quick introduction to what exponential functions look like, what those curves look like. One of the main things that we like to do is look at a relationship and see if that relationship through a table or a set of ordered pairs actually is generated through looking at an exponential or using an exponential. So it says in an effort to see if a relation is a function from a table, you make sure that there's a constant difference between x values and a constant ratio, I should say ratio, not ration, between y values, meaning that you multiply each previous term by the same number to get the next term in the list. All right, so to determine whether something is, let's say linear. If you remember the linear process that we went through, and a lot of times, I think when we saw those back in chapters 3 and 4, like this was x, this was y. If these were increasing by the same amount, so for the most part, we would see them increasing by 1. So it'd be +1, +1, +1. Okay, and if I said, let's say that this was like a 3, let's go 6, 9, 12, 15. These are now all increasing by the same +3. Okay, when you had the difference in your x's increasing, so you saw a pattern there, and you saw this was a common, call that a common difference. What we did is we said that that common difference is going to be your slope. Okay, so we would write a rule here. We'd say y equals 3x. Okay, now that's not enough here because we got to see does that create these ordered pairs? Well, if I put 0 in for that x, it evaluates to be y equals 0. It's supposed to give me 3. But if y was 0, to get 3, I would have to add on 3. So now I'm thinking that rule might be able to reproduce this list. If I put x to be 0, so it'd be 3 times 0 plus 3, that gives me 3. So that gave me this first ordered pair. If I let x be 1, add 3 to it, so putting that to be 1, so it gives me 3 plus 3 gives me 6, gets that ordered pair. Now I'm going to try 3 times 2 plus 3 gives me 6 plus 3, which is 9, gives me that ordered pair. So if you remember that from earlier in the year, that's how we developed and determined whether something was linear or not. We were looking at to see if this common difference of +3 all the time was the same. Okay, when the increase here was always the same. With exponentials, it's a little bit different. With exponentials, this is what we have to do. With exponentials, we're still going to look at the x's and make sure that they are doing the same behavior. +1, +1, +1. Now, they don't have to always be +1. They could be +2, +2, +2, +3, +3, +3. But we need to see a particular pattern with those x's. Then what we want to do is see if what can I multiply -1 by to get -3. My hope is that you see it that as times 3. The question then is if this is exponential, then that times 3 needs to be the same thing that's going to take me from this term to that one. So if I take -3 and multiply by 3, does it give me -9? And it does. Now -9, do I multiply that by 3 again to get -27? And we do. Okay? So this means we have so that's a constant difference in x values And this is then what we call a common ratio in y values. Okay. We'll spend maybe a little bit of time later this week actually coming back and writing the rule then for this exponential. Same thing here. Look at that. Plus 1. Plus 1. Plus 1. And now think about what can I multiply 2 by to get 8? Well, that's times 4. If I multiply 8 by 4, does it get me to 32? In this case, it does. If I multiply 32 by 4, does it get me to 128? And it does. So this one is exponential. So yes, exponential. Yes, exponential. Now we want to look at this last one. Again, we see the plus 1 for the x's. And now here, what can I multiply 0.5 by to get 1? Well, if I double it, that gives me 1. What if I double 1? Does it give me 2? If I double 2, does it give me 4? So this is an exponential because we're seeing that common ratio when we recognized a common difference within the x's. So all of these were examples of exponential functions. A common practice is to just evaluate an exponential when they give me an x value. So when I want y equals 6 to the x, but x is 2, what they're asking is to find that. Well, what would y be? 6 squared ends up being 36. Same thing here, y equals, now it's 2 times, it'd be 0.4 to the negative 2. Okay? Remember, when I substitute that negative in here, okay, or I guess the negative 2, it goes only to the object that is directly behind it. It's only behind the t right now. Okay? So just working a little bit with this, think about our laws of exponents that we've been talking about. Hopefully it makes sense that we would have actually 2 over 0.4 squared. That's how that's really going to evaluate. Okay, 0.4 squared is 0.16. Okay, we have 2 divided by 0.16. Now with that, it does make sense to maybe grab your calculator. And so 2 divided by 0.16 gives me actually 12.5. Okay, so that's how that's going to evaluate. And again, I just took this on my calculator. And then the next one is y equals 2/3 to the x. So y equals 2/3 to the x, but x is 3 now. Well, we've been doing this. That means we're going to have 2 to the third over 3 to the third. When I do this power to a power rule that we've been working on the last couple days. So it gives me 2 to the third, which is 8, and 3 to the third is 27. So that thing evaluates to be 8/27. The next one is kind of a story problem. You usually see story problems that deal with money. When you do interest on mutual funds and those types of things, when you get in the stock market or savings accounts, they grow exponentially if we have what we call compound interest. That'd be something you guys probably talk about in maybe an Algebra 2 class. But this has an investment of $5,000, doubles in value every decade. So after 10 years, this is going to become $10,000. After 20 years, it then becomes $20,000. In 30 years, it would be $40,000. Okay, so it's doubling. And that the idea, if I look at, let's just kind of validate that with Desmos here real quick. If I start with, what did it say? It said 5,000 times 2 to the x, but I can't use x because it'll graph it. I don't want the graph, so I'm just going to use a instead. Okay, and now I'm going to say, okay, well, what if a was 0? Okay, that means I would have $5,000. Okay, so 2 to the 0, remember 2 to the 0 would be 1. 5,000 times 1 is just 5,000. So that would be the initial time. That would be the first, maybe the first decade. Okay. After one decade, you see that $5,000 doubled. Okay. After 2 decades, you see at the $10,000 that I had in the first decade just doubled. Okay. After 3 decades or 30 years, you would see that the $20,000 doubled. Okay. So if we were to really graph this with x, you do see then that behavior of our exponential function. I'll zoom in here. Okay, there's our exponential function doing exactly what we anticipate from the graphs at the beginning. So the question is, how much is the investment worth after 30 years? Okay, so x, when you guys see questions like this, a lot of people want to say, well, let's put in f of 30 and see what that would be. I want to explain why that would be wrong. As we read this, it says x is the number of decades. Well, if you just put 30 in then for x, that means actually meaning 300 years. We don't want 300 years, we want only 30 years. Okay? So what x is in this case 3. I'm talking about 3 decades. So now we'll have 5,000 times 2 to the 8, or 2 to the third is 8. So 5,000 times 8 is $40,000. Okay, so if I start with $5,000 and they tell me that this investment will double every decade, in 30 years, that $5,000 without me having to do anything, that $5,000 has become $40,000. Okay. When we increase like that, it's called exponential growth. Okay, so exponential growth is experienced when this number out front here, this A number, is between or is bigger than 0, so it's positive, and this B value is positive. So these two numbers have to be positive. Okay, so you would see something like maybe y equals like maybe 2 times 3 to the x. That would be growth. Maybe you see y equals, instead of a 2 out there, maybe it's a 1 times 3 to the x. Okay, so a lot of times you would just write that 3 to the x. That would be growth because these numbers, 1 and the 3, are both positive. It would be decay, exponential decay, if then this number here is positive, but the b value is between 0 and 1, so that b value is a fraction. So like something like y equals, let's just say 1, that's my a value, times 1/3 to the x. That would be decay. That means after a time period, my y values are getting smaller and smaller. Okay. In science, you might talk about things like radioactive materials. They decay over time just by sitting still. They kind of dissolve. Okay, their mass disappears. That's what we call it, radioactive decay. If you have invested in a stock or something like that that is not doing well and it's losing money, usually it will decay exponentially. This here is a image that'll help us remind ourselves what these components are for our equation or for our function. Okay, so x is obviously the exponent. B is the thing that is going to decide whether it's growth or decay. Essentially, B, like I said, if it's bigger than 1, it's going to be growth. Okay, so bigger than 1 is growth. Between 0 and 1 will be decay. This is the initial. This A value is the initial amount when x is 0. A lot of times it's 1, but if we had a curve here like this, where right there, let's say right there we have, so this is an exponential, maybe it looks something like that. That value there would be, because x is 0, then the amount on the y-axis would be 3, so my a value would be 3. Okay, I'll kind of give you a demonstration of that real quick here with something like this. Let's go y equals 3 times, let's just go 2 to the x. And you see now, instead of going through, so 2 to the x looks like that. It was always going through 0, 1, but instead of a 2, now we got a 3 out in front being multiplied by that. So it's going to make that now my first amount. Okay, my first order pair when x is 0. And you'll investigate that much more when you get into Algebra 2.